One server goes down and your entire website is offline now. A load balancer can prevent that from happening. A load balancer sits between users and servers and distributes incoming requests so that no single server gets overloaded. Instead of one server doing all the work, the load balancer spreads the traffic across multiple servers, improving performance, availability, and reliability. It also monitors server health and stops sending traffic to failed servers. To decide which server gets a request, load balancers use different algorithms. Round robin is the simplest load balancing method. Incoming requests are distributed sequentially across all the available servers. The first request goes to server 1, the next goes to server 2, the third request will go to server 3, and once the last server is reached, the cycle restarts from server 1 again. This approach works best when all the servers have similar hardware and performance, as it distributes traffic evenly without considering server load. Least connections algorithm routes traffic to server with fewest active connections at the moment. For example, if server 1 has 10 active connections, server 2 has 11 active connections, and server 3 has 6 active connections, new requests are sent to server 3. This method is ideal for applications where session durations vary, as it dynamically balances load based on real time server usage. Least response time algorithm prioritize servers with the fastest response time while also considering their current connection count. A highly responsive server receives more requests until it reaches capacity. Once overloaded, the request is redirected to next fastest server. Least response time algorithm is effective when fast user responses are critical. IP hash algorithm determines the target server by applying a hash function to the client's IP address. The same client IP always maps to same server, ensuring request consistency. For example, if a client's IP hashes to server 2, all the future requests from that client are routed to server 2. This approach is useful for applications that store session data locally on servers. Weighted algorithms assign a capacity based weight to each server, allowing more powerful servers to handle more traffic. For instance, a server with 64 GB RAM receives more requests than one with 16 GB RAM. Geographical algorithms route requests to server closest to user's location. Users from Europe are directed to European servers, while users in US are routed to nearest US data center. This method is commonly used by global applications to reduce latency and improve performance. Consistent hashing is a technique used to distribute requests across servers in a way that minimizes reassignment of requests when servers are added or removed. But why we need consistent hashing? What is the problem with traditional hashing? To handle the load efficiently, we distribute incoming requests across multiple servers using a hash based load balancer. The approach hashes the request, mainly it hashes client IP and assign it to a server using the formula hash of IP mod of n, where n is the number of servers. When we add or remove a server, it completely disrupts the existing mapping, causing most users to be reassigned to different servers. As the n changes, that is, number of servers changes, the formula changes. The solution is consistent hashing. Here we have a circular hash space. Each server is assigned a position on the hash ring by calculating hash of server ID. A request is assigned a position on the ring based on hash of client IP address. The request is routed to the first server found clockwise from that point. That server handles the request. Now we have added a new server, that is S3. So all the requests between S1 and S3, that is U4 here, is mapped to S3 because when looking from U4, S3 is the first server it is encountering in clockwise direction. Other than U4, no other request is required to be remapped or readjusted. Another case is we are removing a server. We are removing S3 from the ring so that U4 is mapped to server S0. Because if S3 is not there, S0 is the first server, U4 encountering in clockwise direction. Here also, other than U4, no other request is required to be remapped. Types of load balancers. Software load balancers. Software load balancers like Nginx, HA proxy, or traffic are installed on servers to distribute the traffic. They give full control, but scaling and failover must be handled manually. Cloud load balancers. Cloud based load balancers like AWS ALB, Azure Load Balancer, and Google Cloud Load Balancer are fully managed cloud services. They automatically handle scaling, health checks, and high availability, which is why most modern systems prefer them. Hardware load balancers. Hardware load balancers like F5 are physical devices used in data centers. They offer very high performance but are expensive and less flexible. Thank you for listening. We will see for next session. Until then, happy learning.